Welcome, my friends! In this video, we will discuss p-values and the hypothesis testing steps. P-values are one of the most important things to understand about hypothesis testing, and are unfortunately highly misunderstood. The best way to understand p-values is through an example. Let's say the mean of some population is stated to be 20, but we believe 20 is too small. The null hypothesis might be mu is less than or equal to 20, and the alternative hypothesis might be that mu is greater than 20. The alternative hypothesis reflects our belief that the stated mean of 20 might be too small. We think the mean is greater than 20. Since the alternative hypothesis has a greater than sign, that means we have a right-tailed test. For the purposes of testing the hypotheses, we assume the null hypothesis is true, and in our case, we assume the null distribution has a mean of 20. The equal to part in the less than or equal to sign in the null hypothesis. Then we go out and take a sample and calculate a statistic, in this case x bar, the sample mean. If the null hypothesis is true, we should expect to see a sample mean close to 20, but if the alternative hypothesis is true, we might expect to see a sample mean higher than 20, somewhere in the right tail of the distribution. Let's say the sample mean is 21. The value is greater than the hypothesized value for the mean, but is it big enough to discredit the null hypothesis? It could be due to chance that we got a slightly higher sample mean than the population mean, or it could signify that the stated population mean is wrong. Suppose the probability of sampling x bar greater than 21 from this distribution is 0.15, or 15%. This would mean that, assuming that the null hypothesis is true, there is a 15% chance of drawing a sample of this size with a mean of 21 or higher. Somewhat unlikely, but perhaps not unlikely enough to discredit the null hypothesis. Events like this, or even more extreme events, happen on 15% of samples, assuming that the null hypothesis is true. But suppose the sampled x bar is 22. Perhaps this results in a probability x bar is greater than 22 of only 0.01, or 1%. If the null hypothesis is true, and the mean really is 20, receiving an x bar of 22 or higher is very rare and only happens in 1% of samples. This might give us a good reason to question the null hypothesis, and perhaps adopt the alternative hypothesis. This percentage is what we call a p-value, and is defined as the probability of observing results as extreme or more extreme than those observed in our sample, under the assumption that the null hypothesis is true. By more extreme, I mean further in the tail of the distribution than the sampled statistic. You may remember that the level of significance, alpha, represents the probability of rejecting the null hypothesis when it's true, what is called a type 1 error. The so-called decision rule in a hypothesis test is that if the p-value is less than or equal to alpha, we should reject the null hypothesis. If the p-value is greater than alpha, we should fail to reject the null hypothesis. The level of significance is a value set by the researcher prior to conducting the test. Setting a lower level of significance, like 1%, makes it more difficult to reject the null hypothesis, but also reduces the chance of making a type 1 error. You can remember the decision rule through this little saying: if the p-value is low, the null has to go. If the p-value is high, the null will fly. If the p-value is low, the null has to go, means that we should reject the null hypothesis when we have a low p-value, lower than the level of significance. If the p-value is high, the null will fly, means that the null hypothesis should not be rejected when we have a high p-value, when the p-value is greater than the level of significance. Now, for a left-tailed test, we look at the probability in the left tail, the probability less than our calculated statistic. This would be when the hypotheses look something like this: mu greater than or equal to 20 and mu less than 20. The p-value is now in the left side of the distribution. For a two-tailed test, such as mu equals 20 and mu is not equal to 20, we care about both extremes of the distribution, so simply take the one-tailed p-value and multiply by 2. Since all of the two-tailed hypothesis tests we will be working with are symmetrical, the corresponding tail on the opposite side of the distribution is equal, which is why we can multiply by 2. For example, if the left-tailed p-value is 1%, the two-tailed p-value will be 2%. If the right-tailed p-value is 5%, then the two-tailed p-value will be 10%. For two-tailed p-values, always start with the probability in the tail corresponding to the side of the distribution the statistic is on. For example, if x bar was 19, calculate the left tail first and then multiply by 2, since 19 is below 20. If x bar was 21, we would calculate the right tail probability first and then multiply by 2, since 21 is above 20. Okay, now that we have covered p-values, we are ready to summarize the 5 steps of any hypothesis test. Keep in mind that different instructors might include different things in the 5 steps, so make sure to use the steps covered in your class. For us, step 1 is to check our assumptions or conditions. The exact assumptions or conditions will depend on the test, but typically include at the very least a random sample for use in gathering the data. Step 2 is to set up the null and alternative hypotheses. For most tests, the null hypothesis will have one of these 3 symbols, which indicate equality: greater than or equal to, less than or equal to, or just plain equal to. The alternative hypothesis will have the opposite sign of the null hypothesis, either less than, greater than, or not equal to. Depending on the sign in the alternative hypothesis, the test will be classified as either a left-tailed, right-tailed, or two-tailed test. Less than in the alternative hypothesis suggests left-tailed, greater than suggests right-tailed, and not equal to suggests two-tailed. The wording in the problem will help you determine which of these 3 tests is most appropriate. I'm using mu in these hypotheses, but hypothesis tests can be done on parameters other than mu. Mu sub 0 is just some hypothesized value for the mean, which will take on a real number when we complete an actual test. Step 3 is the biggest step, which I like to call calculations. This step begins by determining the level of significance. Then we calculate a test statistic. In general, a test statistic is a number calculated based on a sample in a hypothesis test in terms of some corresponding distribution, such as the z distribution, the t distribution, the chi-square distribution, or the f distribution. You are probably familiar with the z and t distributions, and we will discuss the chi-square and f distributions in future videos. For example, if we are completing a hypothesis test based on the mean with a known population standard deviation, the test statistic would be found by using the formula z equals x bar minus mu divided by sigma over the square root of n. Then a p-value must be calculated using the test statistic. For example, using a z-score, we would use the normal CDF function on the TI-84 calculator to calculate the p-value. It might be helpful to draw the distribution in this step to help understand where the p-value and the test statistic fall on the graph, as we discussed earlier in the video. Step 4 is the decision rule, which I mentioned earlier. If the p-value is less than or equal to alpha, we reject the null hypothesis. And if the p-value is greater than alpha, we fail to reject the null hypothesis. Finally, step 5 is the conclusion, which amounts to completing this statement. At the alpha % level of significance, there is or is not enough evidence to suggest that, and then insert a description of the alternative hypothesis. Use is when the null hypothesis is rejected, and is not when we fail to reject the null hypothesis. So an example might include this set of hypotheses, and a conclusion for failing to reject the null hypothesis might be, at the 5% level of significance, there is not enough evidence to suggest that the population mean is less than 20. Notice I use is not instead of is, as this is a conclusion where we failed to reject the null hypothesis. Alright, my friends, that wraps up part 3 of our introduction to hypothesis testing. We will be looking at how to apply the 5 steps to specific hypothesis tests in the next several videos.